Okay.
Hello, hi everyone, good day. Welcome to the Geoscience and Geoenergy webinar of today, 3rd of March 2022, 3/3/2022. So 3/3/22. Um, Today, Sebastian and myself both from TU Delft. So we took him as hostage or stole him. I don't know what's the proper expression. So he's actually sitting about 5 meters away from me.
I
And,
came very much voluntarily, Hadi. I came voluntarily.
and we meet each other in the corridor and take coffee together. So it's quite nice. So both of us from TU Delft Geoscience and Engineering Department are pleased and delighted to host you all today. We hope all of you are safe, happy, and in peace. Um, and also, today we have the pleasure and honor to host our first distinguished speaker from Brazil. Location wise, we have had Brazilians speaking in this. We have tried our best to be as diverse and inclusive as we could, but also we have the pleasure to have Professor Grigori Chapiro today with us, location-wise located in Brazil right now. We wish we could have been there already ourselves, but still it's nice to have him online. Grigori is Associate Professor at the Department of Mathematics in Federal University of Juiz de Fora in Brazil. Grigori is head of the Laboratory of Applied Mathematics. Over the past several years, he has been studying porous media flows and transport phenomena of different types with a mathematical perspective. He holds a PhD from the Institute of Pure and Applied Mathematics, known as IMPA, in Rio de Janeiro, in Brazil. He has received a number of awards, including Interpol National Chapter Award in 2020, which was awarded to him as part of the board coordination of the Brazilian chapter of Interpol. He also received Productive Brazilian Scientist Award in 2020, which is granted by CNPq to Brazilian most productive scientists. Also, he has received a supervision of the Best PhD Thesis Award in 2019 and second place in national exam for bachelor graduate students in 2002. He was also visiting professor at TU Delft in the same department Sebastian and I are working between 2013 and 14. And 13 was the time I joined TU Delft, so I know him very well during those period. His research interests are mathematical and computational modeling of foam injection, and also especially as an EOR technique applied to Brazilian pre-salt reservoirs, and also mathematical formulation of combustion in porous media and biomathematics. His Google Scholar page is listing all the publications he has. We are going to send it also to the chat box so that if the audience are interested, please get in touch with him for mutual collaboration, work, questions, etc. And without any further ado, I'm going to hand over to you, Grigori, to start your lecture. But please, the audience note, his lecture would last for about half an hour. Do type your questions in the chat box. Sebastian, my colleague, uh, will take the questions and feature them, and we are going to hear Grigori's comments on them. Thanks very much, Grigori, for accepting graciously our invitation, and we are very much looking forward to hearing your talk.
Okay, thank you very much for this kind introduction, Harry. Also thanks Sebastian for both of you for invitation. So today I'm talking about this presentation is a little bit outline of the common geoenergy talks because I will talk mainly about mathematics. But I promise to try hard not to bother too much everyone. So I will talk about the mathematics aspects of modeling the foam flow in porous media, and specifically the question whether these models are Newtonian or not Newtonian. So first of all, this is a joint work with a number of colleagues, and I'm really sorry if I forgot someone. Well, some of our ex-students are already abroad, and there are a lot of people from other universities, so this is an interesting topic. Well, including people from TU Delft. So the brief outline of my talk, I will explain really briefly, motivate what is foam and porous media, and then we will see some comparison, so some example of foam flow which is quite Newtonian, and then we will see uncertainty quantification sensitivity analysis for the foam which is non-Newtonian. And last but not least, we'll try to understand how much non-Newtonian can this flow be. So first of all, what is foam in porous medium? Then it's basically, we have these lamella, which are these thin liquid films separating gas bubbles. And the main property is that the foam reduces drastically the gas mobility. So, and how we, like our talk, this talk is mainly centered in mathematics, so the foam texture is modeled as a tracer in the gas phase. So we don't have foam as a separate phase, it's part of the gas phase. And another issue, another property interesting for foam is that it doesn't affect water phase relative mobility. Now, foam has a lot of applications, including soil or aquifer remediation, EOR, so in-install recovery, CO2 sequestration, others. And here I bring a picture about EOR just to evidence this utility. So for example, if we inject water to displace oil, it will form this type of structure which is called fingering. And here we have also gravitational override, so which is not so good. But then, for example, in Brazil, we are using a lot of WAG and SAG techniques, so the techniques which alter gas and water injection. But if you inject gas to displace oil, there will be even worse fingering on the other side due to gravitation as well. So foam injection can not solve but remediate this issue by reducing drastically the gas mobility and trying to increase the swipe efficiency of this structure. Okay, so here we can see the result of numerical simulations for foam displacement. This was done using by my colleagues and myself by using our in-house built simulator for specifically for different foam models. And on the upper picture, we can see the gas displacement, so gas displacing water in porous medium, in heterogeneous porous medium with gravity. And you can see that the gas flow freely. And then picture below, you can see quite well-defined foam front, so gas front, swiping the reservoir of water. Okay, so what is non-Newtonian fluid? The basic definition of non-Newtonian fluid is a fluid doesn't follow Newtonian law of viscosity. So its constant viscosity is independent of stress. And then this picture, the left picture, is a classical one, which explains how shear rate and shear stress behave. So Newtonian is the straight line, which means that they depend linearly one with each other. And well, for those who entered this seminar without knowing what is non-Newtonian fluids, we have them all around us every day. So the most famous are ketchup, which is really hard to take out of the bottle in right quantity, and the corn flour with water, which behaves really nice, and you can search YouTube videos for it. You can even run on water with corn flour if you run fast enough. Well, so let's go to approach slowly the modeling part. The behavior of foam is frequently reported as shear thinning. So from the previous slide, we saw that this means that the apparent viscosity decreases with increased shear stress. And there is this nice derived formula by Hirasaki and Lawson in 1985, which relates this apparent gas viscosity. I remember that in this case, when we say gas viscosity, we model foam as a part of the gas phase. So this gas with foam, right? So gas with foam viscosity, how it depends of foam texture, ND, and how it depends of the gas phase speed, UG. Well, and actually this formula is consistent with the first, maybe in the classical result by Brethenton of 61. He did experiments using isolated bubbles, and yeah, and it has, okay, and the form, as we say, this formula is used in a number of models describing foam displacement porous medium. Well, now about Newtonians, there are a number of works that describe that foam can be quite Newtonian. So, for example, for high quality foam regimes, which I will explain in a minute, and also nearly constant capillary pressure during steady radial flow. Well, here I have to say that it's really hard to do mathematical analysis for non-Newtonian fluids. And until recently, the only basic hypothesis, seminal hypothesis that allow us to prove things for foam flow models was that it is Newtonian. And for different experiments is compatible with experimental data. Okay, so let's see what is this experimental data. In the series of paper, Simju and co-authors, actually Simju did his PhD at TU Delft under supervision of Professor Zita. They did a lot of experiments with alloy surfactant, nitrogen gas, betimer sandstone, and the gas and water solution was injected from the bottom of the core, generating foam, and it was measured by using X-ray CT scan. Of course, in these papers, you can find a lot of details. Now, the model used to describe it was proposed by Professor Zit in 2006. It's called Stochastic Bubble Population Model by the authors. And it's a quite standard model. So we have here, we have a balance for water mass balance law. And this is Darcy equation, and here is the foam balance equation. So as I say, foam balance equation here, it should be, well, sorry for this, here should be, let's call it NGSG. So it's a tracer in the gas phase. And the important thing is that foam has destruction or coalescence and generation term. And usually this term basically can be written as the difference between the foam at the present situation and the foam at local equilibrium conditions. Of course, and this simple model doesn't take oil into account, so we have only foam and water and gas. And here is non-Newtonian Hirosaki-Lawson equation for viscosity, and the rest doesn't matter right now. So this is a nice model. Unfortunately, we cannot solve it mathematically. So what we did was to eliminate Darcy equation. So we consider constant total velocity. And in the next few slides, we will consider that the flow is totally Newtonian. So we don't consider this Hirosaki-Lawson equation. Now, how we do it? We consider that the total relative mobility of gas is corrected using foam for some mobility reduction function. So MRF stays for that. And this mobility reduction function is just a function of foam texture. And now we equate both mobilities for using Hirosaki-Lawson equation and without it. And we try to estimate the coefficient beta. We substitute some average velocity, and then we obtain this constant. Of course, more details, I'm here just summarizing. You can find more details in the paper by Zavala and other co-authors in Transporting Porous Media past year. So if we substitute all these hypotheses, we arrive at these partial differential equations, where again, the first one is mass balance of water, and the second one is foam texture. With the source term, as I described, I'm calling attention here for the source term because we'll change it in a few slides. So just remember, this is a typical model for foam displacement in water and gas. And what will change mostly is the equation for gas viscosity, and the source term. And to solve this equation, we will use initial data. So here we consider Riemann problem, which is simply the nice name for the step function. So we have some constant for the left, constant for the right. So it approaches the situation in a one-dimensional long tube, which we have some initial condition in it, and we inject some another condition. Okay, now how we will solve it analytically? We will use the so-called traveling waves. And what are they? I'm trying to explain this in a very simple way. So if we have the partial differential equation like this, we transformed it in 3 simple steps. So first of all, we change the variables to the traveling variable. You can think about it as a Eulerian Lagrangian change of coordinates. So the coordinates which travel with the wave will be eta, which is x minus vt, where v is a constant traveling wave velocity. Now, by changing this, we arrive at the ordinary differential equation system. And now we will consider stationary solution of the system, which means stationary. It means that we just neglect this red term. Well, and the third step is that we need to join, so the Riemann problem, the initial Riemann problem for the previous slide, so the step function. So this OD needs to satisfy the asymptotic boundary conditions given by this Riemann problem from the previous slide. If you're interested in studying traveling waves, I recommend the book by Wolpert and co-authors by American Mathematical Society. So substituting, like I explained before, in the system of partial differential equations for foam, we come to this sympathetic system of ordinary differential equations in traveling variables, which describe now the ordinary differential, so the traveling wave solution of this of the foam traveling wave in porous media. We have to solve it for, as I say, for these boundary asymptotic boundary conditions. And of course, keeping all mathematics from the system, we can obtain analytical formula for traveling wave solution, well, for traveling wave velocity, which is nice because we can check it also for experimental data, for example. Now, if we compare this analytical solution on the left, so for Newtonian, as I say, it's a simplified Newtonian model, and we compare it to numerical solution for the original model, so non-Newtonian one, we can see that qualitatively they are quite similar. And actually, as we will see in a second, the speed is also very well captured. So here we can compare the same analytical solution in blue with the green. Green are the CT scan obtained experimental data, and we can see that qualitatively it's well captured, and moreover, for the final times, the speed of the wave is captured correctly with this analytical solution. And actually, the initial steps are not so important because also numerical solutions and experimental data, they take some time to stabilize a stable front. So we are not so upset about that our analytical solution doesn't fit very well the initial data. Okay. What we can learn from this example is it was an example where Newtonian simplified model can describe quite well the experimental data. Now let us see the same things from different perspective. So now we will consider different model. In this work, we consider the model implemented in commercial simulator STARS by CMG. And it's very similar. However, it's a little bit simpler in the sense that the foam texture is considered to be in equilibrium. So there is no separate equation for foam texture balance. It's already considered as a known function of the water saturation. Another difference is that it also uses mobility reduction function, MRF, and it's given like this. And I, highlighted the terms in red, which corresponds to the non-Newtonian terms in this model. So we want to know how this shear thinning force is acting for foam displacement. And of course, this paper is not about non-Newtonian flow itself. It's about the difficulties in fitting. So we use uncertainty quantification and sensitivity analysis to obtain best option for fitting parameters from experimental data into commercial simulators. And these are real difficulties that appear when you try to do it. So just to explain, this is not real part of our talk, but just to explain what will appear in the next slides, in this paper we propose different objective functions, and we improved quite a lot the fitting, how to fit experimental data into simulators. So, but what I want to show you is that either with all these objective functions, well, you can see that here, this is a graphic of, of mobility reduction factor, so MRF, and how it works, how it goes with foam quality. And this curvature is more or less corresponds to non-Newtonian model, which is not clear in this slide, but it will be clear in the next one. So here we obtain the distribution for parameters of the model, and you can see this EPCAP. It was red in the previous slide, so this corresponds to the non-Newtonian part of the model, and it's like just 0.5, quite with huge good concentration. So the model is indeed non-Newtonian. Moreover, we can present the sensitivity analysis. So in these graphics, what interests us is the EPCAP, so the green curve, and we plot the dashed and solid lines corresponds to main Sobol index and the total Sobol index, which corresponds to local sensitivity analysis or global sensitivity analysis. And either way, we can see that for the high quality, this model implementing stars is not the non-Newtonian behavior. It's not so pronounced, and very low foam quality also. So the foam flow in model implementing stars, it is not Newtonian, non-Newtonian. It's not Newtonian for very low or very high foam qualities. And as I say, this data quite well relates with what found in the literature. And now the question is, okay, we saw one example where the foam is Newtonian, another example where the foam is non-Newtonian. Now let us try to understand when it's Newtonian or not. So what we did in this work was to take another model, which is similar to model by stochastic bubble population model. And then we consider the difference is that the source term is given by this function where which is almost the same as before, but the foam in equilibrium is not a constant, but a function of critical water saturation. This model was proposed by Ashoori and co-authors in 2011, but here we consider Hirasaki-Lawson's formula for gas viscosity. What we did in this work, we managed to solve it analytically, so for the first time, and we try to obtain our goal now was in fact compare Newtonian and Newtonian models. So we propose a function how to do it. And the proposition is to minimize the mean square difference between gas mobilities for both models. So by this way, we can make more general. So it's a procedure that every model we can now compare Newtonian and non-Newtonian version of it. I hope we can. This work will be public soon. Now it's under review. And by using this function, we can compare now Newtonian and Newtonian models. These graphics are these L functions, L graphics, which are quite famous. So on the left, we have the non-Newtonian shear thinning. Each line corresponds to isolines of pressure gradient, so some constant pressure gradient. And on the upper picture, you cannot see really the difference, but if you plot it in a log scale, here these green dashed lines corresponds to the foam quality or the FG function of 2.49, and we can see that it intersects the constant speed isoline in quite different places. So using this type of analysis, we can actually obtain the conditions, so the injection saturation, which corresponds to the biggest gap from Newtonian and non-Newtonian models. And then we can analyze two scenarios. So the first scenario, before that, just to show another application, we can see that we can plot now the apparent viscosity for different total velocities. And exactly, so this dashed line corresponds to Newtonian model for this FG. And for different FGs, we can see different lines. And exactly like for the previous paper, so again, it agrees with the previous results. For the high quality regime, so these ones, we have a straight line. So basically the behavior is Newtonian. And for really low quality regimes, it's also approached Newtonian. Now, if we consider, so let us, to finish this, let us consider two scenarios. So the first one is from the original paper. So this is more or less experimental data. And again, we see that these are profiles for water saturation and foam texture. And we see that they coincide actually pretty well. And the speed also coincides. So this basically shows that the original data is quite Newtonian. And this is a scenario one. So our solution, analytical solution for non-Newtonian using traveling waves, coincide with analytical solution for traveling waves using Newtonian version of the same model. Now you can see that these three pictures correspond to different coefficients, parameter coefficients for KC and saturation injection. It seems a little bit strange here. I don't have time to explain how these type of solutions appear mathematically in the model. But if you're interested, please visit this paper. We obtain there and explain quite in detail how to obtain these mathematical solutions from the foam models. Now, the second scenario, so the worst case scenario, let's call it, because it's not worst case in the sense that it's a most non-Newtonian, which this scenario, which the foam regime that this model allows us to do. So here we can see also both water saturation profiles and foam texture profiles. And we can see that here the qualitative solutions are quite different, and also the wave speeds differ. Well, just to summarize, I think I'm coming to the end of my 30 minutes. Well, for high quality regimes and for very low quality foam quality regimes, both sensitivity analysis and traveling wave solutions point that foam flow is very well described as Newtonian by all these models. So secondly, we propose a procedure to compare any model, Newtonian version of it versus non-Newtonian version of it. And it works well. So for the models which are Newtonian, in a regime which we expected from other papers and other works to be Newtonian, it works very well. So, and we can use it to compare how non-Newtonian certain models of certain regimes are. And finally, by using traveling wave solutions, we can try to quantify how much non-Newtonian behavior you can extract from these models. And we can summarize it as, so the biggest relative difference in pressure gradient was about 39%, and the traveling wave velocity was 11%. The relative difference was about 11%. So that's it. Thank you very much for attention. And of course, thanks a lot for our sponsors. Without them, we cannot do research. So thank you, Heidi, Sebastian, everyone who paying attention.
Thank you very much. You were perfect on time. So we see already plenty of questions posted. Hand it over to Sebastian, please.
Yes, thank you very much also from my side, Grigori, for a really interesting talk on foam. There are a few questions that go to the pore scale physics on foam. I start with one from Yuhang Wang. He says, has there been any pore scale, microscale study to analyze non-Newtonian behavior of the foam flow, considering the complex interface and dynamics involved in the system? So has someone tried to do some modeling or possibly imaging of foam in porous
Yeah,
medium at the pore scale?
yeah, this is a really nice question. I understand that the question if so how non-Newtonian is the form is really huge. So that's why I started my talk. So we are only concentrated on mathematical aspects. So there are already models basically which are in the community and are widely used. So I showed here maybe the most used commercial simulator and other models which are widely used in the literature for simulate forms. And we are analyzing here how much non-Newtonian are these models, right? So, of course, the question about experimental study of microscale is really interesting, but maybe I'm, as mathematician, I'm not the best person to answer it.
Okay, good. I see Bill Rosner's just coming in, so maybe he, with a question, put Bill's question forward in a moment. But Bill may have some thoughts as well on what is out there in the pore scale experimental domain. Just stay on the pore scale side. And yes, you're not an experimentalist, but there's sort of a really interesting set of questions from Willemijn. Hi, Grigori, thanks for the talk so far. I'm not sure how foam should be modeled at the pore scale to appropriately find upscale relative permeability capillary pressure curves. And she then continues asking, my main concern is that the flow does not seem to be steady state at any point. Can you please comment on it? You actually said you assume in your model that the velocity is a constant, so it's steady state, but it's not.
So yeah. Well, again, this type of question arises a lot when you present to mathematical talks to general public. So, I mean, it's really hard to prove anything mathematically. And actually, we managed just a year ago to find a proof find an analytical solution for non-Newtonian form. And I'm really happy to share with you these ideas. This paper is not even published yet. And yeah, so and the assumption that the foam speed is constant is crucial at this point. So unfortunately, we cannot give it up at this time. And about the steady state, so we have two types of model, mechanistic models and foam balance laws. So the stars model I presented here, it's steady state. So we consider that the foam just a function of saturation, but the other two models not. So they are not steady state at any point. So they are actually changing with time. And this, I didn't present it here, but in heterogeneous porous media, it's quite, it makes more difference. The difference is more pronounced.
Okay. I had a question. I'm going to sneak in one of my questions here. So when you showed the different traveling waves, and you said at early time there's a mismatch, but you're not too concerned. You're really more concerned about what's happening at late time. There you get the good agreement. What is the reason for that mismatch at early time? Is that something to do with because you had to make that simplification of assuming a constant velocity?
Excellent question. So the thing is that when we transport, so we are searching for analytical solutions for a system of non-linear, non-Newtonian partial differential equations. So you cannot just go and put it in a calculator, right? And we have to need a lot of hypotheses. So hypothesis of traveling waves, it's a really useful one. You saw it, right? It makes sense, and we can obtain the solution, and it allows us to use a lot of other tools. But it's a stationary solution, so it already assumes a constant velocity by default. And then when you do experiments in laboratory, or you do, so for example, computational simulations, your solution will take some time to stabilize. So if you put just a Riemann problem initial data, and then you expect it to come to some profile, and during this stabilization period, it will change velocity. So the analytical solution by default is constant velocity, but the experimental data and the computational data are not. And then what we expect? We expect that experimental, if we expect that really the experiment have traveling wave solution, it means that after some stabilization time, it will form a front which travels with a constant speed. I'm just saying that it makes sense. So I show you a picture, and before someone says, oh, but it doesn't fit in the beginning, I say, well, the beginning is not important by default, by definition. because the definition is after some critical time, it assumes a constant speed and it travels with constant speed. And this we captured well. Okay.
Great, thank you. So I'm passing over and moving over to some more mathematical questions for you. Kishan asks, hi Grigori, in your 1D numerical results, I think I've seen a few studies which report oscillations in the transport solution when the front is close to the critical saturation value. Would analytical solutions such as yours help numerical simulations to run more stably? Can you comment on that, please?
Yes, so I'm making propaganda of our paper here. It's exactly about that. So the point is that when you run simulations, you actually you can observe some oscillations. And well, I'm sure we have quite an audience. Heidi, for example, here who is from numerical perspectives, are specialists, and you cannot distinguish by just looking at them if this comes from mathematical oscillations or it comes from instabilities in your solution. So what we are helping here, we are saying that exactly there are some kind of parameters which these solutions oscillate. So, and this is not trivial. So if you don't know about these analytical solutions, you cannot build a really stable numerical simulator because you just don't know where is the numerical unstable or when these numerical instabilities appear from actually mathematical data. And what we are working in our lab, we are building an in-house simulator using these solutions as a benchmark. So our simulator exactly captures all this, where it has to oscillate, we know it has to oscillate, it oscillates. And when it don't need to oscillate, it doesn't oscillate. So this is indeed really when analytical solutions can help numerical programming. Now, there is I'm not saying we solve every problem on the Earth, because of course analytical solutions are very strict. So we have a lot of hypotheses like 1D, as you said, constant speed, which you don't want it in commercial simulator, field scale commercial simulator, but you can at least check it in a particular case and see if it works.
Thank you. I was just surprised. Sorry, my camera suddenly became all blurred. Sorry, apologies. Thank you for the answer there. Sarah has a question. Well, she says, sorry, she first says, thanks for the nice talk. And her question, again, sort of more on the numerical side, is that how meaningful are simulation at the reservoir scale, considering heterogeneities, fractures, etc.? Can the U mathematical study help us to advance numerical approaches for 3D reservoir simulation for 3D complex systems?
Yeah, thank you. The questions are really nice. So I think the first question, I think no one has an answer. I'm not sure about that, but I mean, well, it's just a standard now for all oil companies and to make numerical simulations before drilling. I think this is a state of art now, so this is considered to be standard. Now, how it is real, I think, well, up to my knowledge, it's not like we know how, right? We can easily compare it to lab scale experiments, which we did here, but actually even comparing with a field scale experiment is quite hard. So I'm not sure, I don't have answer to your question, but I'm not sure anyone can answer your question fully. Now, the second part again, analytical solutions can help because if we take uncertainty, so like more philosophically, in the sense that uncertainty is not this definition of uncertainty we use here, but uncertainty is we don't know something. So you can have errors, let's say, coming from physical measuring, laboratory measurements. You can have errors from numerical errors. So just some guy put wrong line in 2000 line code, right? And you can have errors coming from mathematics. So you implemented equations and you don't believe that these mathematical equations have some type of solution, which they actually do. So everything in the rest is correct, but your solution oscillates and you think you don't know where to search for your error. So let's think in this huge amount of uncertainties, we are attacking something which not so many groups are attacking. We are attacking the part that how your mathematical solution behave inside your numerical simulator. Okay, so this is a part where mathematics can really help in to commercial simulators to real field scale experiments and industry. Now, of course, there are a lot of other uncertainties in large scale. For example, experimental data comes with comes with uncertainty, right? And then how to measure, how to diminish this, how to fit best parameters into the simulator. We also work on that using uncertainty quantification, sensitivity analysis. This is also not a trivial question. So, and so on and so on. So how to build a better simulator it's also uncertainty. But we are attacking, in this talk, I'm trying to focus on very strict type of uncertainty. And I believe it can help industry and physics and understanding the phenomena.
Thank you. We have stay on the topic of sort of the mathematical aspects of your work before we go back to the physics, then probably for the last two questions. So Bernard Moenbroek asks, hi Grigori, thank you for your nice talk. Is it possible to do a linear stability analysis to investigate the stability of your 1D analytical solution?
Hi Bernard, nice to hear from you. It's a very nice question. We are working on it. So yes, and we are working on it.
Okay.
And yeah, if you have any ideas, I'm open for to talk. But yes, and we have actually. So what we've done in past years, we produced analytical solutions for different models. So and now we are trying to join them to understand what's going on. This talk is part of this joining process, and of course, there is a lot of other things that we can done. And just to use Bernard's question as propaganda, so of mathematics, let's say not computational mathematics. So some things, if you want to understand, for example, sensitivity analysis, if you want to do just numerical simulators, you will run it infinite. You need to run it infinite times, which is impossible by default. So when you have analytical solutions, you can perform this type of analysis analytically. So analytical solutions allow you to obtain some data which is not possible to obtain otherwise.
Thanks. On that discussion, that's really on the topic. It's really nice. There's some interesting comments through here. Luis Fernandez says, hi Bernard. Bill Rosten has an article on this topic, stability analysis of uniform equilibrium foam states for EOR processes. And that's just a comment. And then there's another comment from Bill Rosten himself. He says, on slide 8, assumed flow was limiting capillary pressure, PC star. This was before the realization that there were two flow regimes. In effect, it was a theory for the high quality regime. So we had two comments here on Bill's work. And then Bill perhaps asks, so as a final question for your talk, it says on slide 21, you say foam is Newtonian at very low foam quality. But isn't that partly because a straight line fits a curve fairly well over a short interval?
Well, nice. Hi, Bill. Nice to hear from you. Nice question. Maybe you are right, but also look, we obtained the same result by two ways, right? So this slide is not about the fit on short wave. This is just sensitivity analysis made by using this polynomial Gauss expansion and Markov chain Monte Carlo method. So I don't think here this is important. In the other slides later, I think yes, then it's here. This can be really done, but at least for these values, which are like we are talking about 10 to minus 1 to 10 to 2 micrometers a second, you can see that it has much less curvature. And of course, if I go to 0.00001, it will be even less. So I think you are right, but I think this this affirmative is correct even from the other perspective as well.
Great. Thank you very much again for that question. I think that sort of largely concludes the questions that we had. Bill is actually pointing out to Luis, who commented on Bernard's talk about the paper that Bill Rosten has written on that it was for different foam model. So really lots of nice interactive discussions. And Bill actually says, point taken, the straight line down at slide 21 was just an illustration of the point. So yeah, great. So really nice discussions also happening there in parallel at the chat. Thank you very much again, Grigori, for great talk. Thank you to our audience for some excellent questions and so many active participation in thinking about Grigori's really nice science. And Hadi, over to you for announcing our next week's speaker.
Yes. Thanks a lot, everyone. The next week speaker is Hemo Abels, the next door colleague of mine, a geologist. So we are moving back from Brazil back to Netherlands. Hemo will give a talk about improving prediction of static fluvial reservoir properties using outcrop, subsurface, and numerical modeling analogs. So until next week, 10 March 2022, stay happy, healthy, safe, and sound, and also tuned into our channel for another geoscience and geoenergy webinar. And this time, geology. From mathematics, we move on to geology. So it's quite a thermal stress our audience are observing now. All the best, everyone. And thanks a lot, Grigori. It was a fantastic talk.
Okay, thank you for
everyone.
invitation.
Thank you, Grigori.
Thank you, Sebastian. Thank you, Heidi. Thank you for the audience for the questions. It was my pleasure.
Pleasure. Bye.
Bye-bye, everyone. Bye.